Hello friends. So today we are going to discuss the questions from the year 2007, and from the year 2007 we have total 5 questions. From 2008 we are having 1 question, and from 2009 we are having 3 questions. So in total we are going to discuss 9 questions. So the first question, it was asked in the year 2007, and it states that positive and negative point charges of equal magnitude are kept at 0, 0 a by 2, 0, 0 minus a by 2 respectively. The work done by electric field when another positive point charge is moved from minus a 0 0 to 0 a 0 is. So we have to find out the amount of work done by the electric field, and that electric field will be because of these two positive and negative point charges. Okay. So first of all, let us draw an approximate figure for that. And here we are given that we have point charges, positive and negative, and these point charges are both along positive z-axis as well as negative z-axis. So we can just draw the approximate figure for that. So this is our x-axis and y-axis, and we are going to draw a perpendicular, that is a third axis z, which will be something like this. Okay, so this is our z-axis. So we can say the angle between this and this, they should be of 90 degree. Okay, because this will be vertical in the space, that is our z-axis, and x, y are in the same plane. We have to remember it. And it says that work done by electric field when another positive charge is moved from minus a 0 0 to 0 a 0 0. Okay, so point positive charge is being moved from a coordinate that is given as minus a 0 0, and it is being moved to this coordinate, and its coordinate given as 0 a 0. And we are also given that the positive and negative point charges are kept at 0 0 a by 2. Okay. So somewhere here, so this is our positive charge q, and its coordinate, let us suppose point is our a, and coordinate is 0 0 plus a by 2. And symmetrically on the other side, let us suppose we have this as b, whose coordinate is our 0 0 minus a by 2, and here we are having minus q charge. So it means the electric field will be generated by these two charges, minus a charge at a and charge at b, and a positive charge q is point charge q is being moved from, let us call this as point as c and this point as d. Okay. So in this case we are going to find out the basically so this two charges minus q and plus q are indirectly going to behave like a dipole. Okay. And based on this dipole, which is consisting of a and b, we are going to find out what will be the distance of the point charge, that is our Q, or we can say what is the distance of C as well as D from this dipole. So we are given that we have a positive charge is at the point is given as A, and its coordinate is 0, 0, A by 2, and we have a negative charge that is our B, and its coordinate is given as 0, 0 and minus A by 2. So we can say this will behave like a dipole. Okay. And we have to remember that this is along z-axis, so it is vertical into the plane. Okay, so plus Q is in the air and minus Q is in the bottom side. And we are also given that we have a positive test charge, moved from and it is being moved from minus A 0, 0. This is our C, and it is moved towards D, and whose coordinate is given as 0, A 0. So first of all, we are going to find out what will be the distance from the initial point to both the charges. Okay. So initial point is our C and final point is our D. So we are going to find out the perpendicular distance between BC, and then we are going to find out our AC. Okay. So you can say distance from initial point to both charges, and this initial point is our C. So first of all, we are going to find out our CB, and then we have CA, CB, one and same thing. Okay. So we say distance from minus A 0, 0 to 0, 0 A by 2. Okay. So we start with minus A 0, 0 to 0, 0 A by 2. Okay. So we can say we are finding the distance our CA. Distance CA we are going to find out, because this point is our C and this point is our A, and that we can use simple distance formula, and according to that we get minus A, 0 whole square plus 0 minus 0 whole square plus 0 minus A by 2 whole square and its square root. This will be equal to, we get this as A square plus A square by 4 and square root, this comes as square root 5 by 2 times A. Okay. So we got this as distance CA. Okay, let me write it here. So we got distance CA is equal to square root 5 by 2 multiplied by A. Next, we are going to find out our next point is our B point, CB. So we start with our minus A 0 0 and 2 0 0 minus A by 2. So this start with C and end at B. We can call the distance our CB, and same formula, that is our distance CB will be equal to minus A minus 0 whole square plus 0 minus 0 whole square, and this comes as plus 0 minus of A by 2 and whole square and its square root. So this will be coming as our A square, and this will be also coming as A square by 4 and its square root. So we get our DCB will be equal to, this comes as square root of 5 divided by 2 multiplied by A. Now for the final point. Final point is our D point. So you can say the distance from final point to both charges. Distance from final point to both charges, and here final point is our D. So first case, once again we start with our D, that is 0 A 0 and up till 0 0 A by 2, and 0 0 A by 2 is our A. So we found out here D to A, or we can say distance of D to A. So we can use distance of D to A will be equal to, we have this as 0 minus 0 whole square plus A minus 0 whole square, and this comes as plus 0 minus A by 2 whole square and its square root. And once again this will be coming as A square plus A square by 4 square root. We get distance of DA will be equal to square root of 5 divided by 2 times A. And finally our last point, that is from 0 A 0 to 0 0 minus A by 2. It means from D to A, sorry, not to D to A but D to B, that is a minus. We can call their distance from D to B. So we get distance of D to B will be equal to 0 minus 0 whole square plus A minus 0 whole square plus 0 minus of minus A by 2 whole square and its square root. This will be coming as A square plus A square by 4 and its square root. So we get our distance from D to B is equal to square root of 5 divided by 2 times A. Okay. So we can, from all these distances, if you make the comparison, we clearly see that the distance of both the charges are equal. So therefore the potential at both the points is 0, okay, because point is equidistant from both the charges. You can say that distance to both charges are equal. Therefore, we can say that our initial potential Vi will be equal to 0 and our final potential will be also equal to 0. So work done. That is that W will be equal to charge, test charge, that is Q, and we have V initial minus V final. Obviously that will be equal to 0, so work done comes out equal to be 0. Therefore, the option number C is the correct one. Option C is correct. Next question. It was also asked in 2007, and it states that consider a neutral conducting sphere. A positive point charge is placed outside the sphere. The net charge on the sphere is then. So here we have to find out the net charge when a positive point charge is placed near the outside the sphere somewhere. And it states that initially that is a neutral conducting sphere it is. Okay. So for the sake of simplicity, let us consider this is a sphere and a positive point charge. Let us suppose this is our positive point charge, that is our plus Q, and because of this plus Q, it is going to attract the electrons from the sphere. So on this side we are going to have the minus Q, and on the opposite side we are going to have plus Q. Okay. And initially it is given that the sphere is neutral. Okay. So we can write that initially sphere is neutral. So which basically means that total charge on the sphere is 0. Total charge on sphere is equal to 0. And when the positive charge is brought near the sphere, then it is going to attract free electrons in the conductor toward itself. Okay. Or we can say it will be redistributed basically. We can say when a positive point charge is placed outside the sphere, so because of this, the free electrons in the conductor redistribute. Okay. And by redistribution we means that the negative charge, which is basically in electrons, will be attracted towards the side of the sphere closer to the external positive charge. Closer to external positive charge, and the positive charge will accumulate on the opposite side, will accumulate on the opposite side. And this is basically nothing but electrostatic induction in the shorter form. Okay, this. But in this case, although there is a redistribution of the charges, or basically free electrons on the sphere, the net charge is still 0 on this sphere, because no charge is added or removed from the sphere. That's the most important part. Okay. So from here we can say that no charge is added or removed from sphere. Therefore, we can say that the net charge remains 0. Net charge remains 0. Or in terms of conservation also, we can make an assumption that initially the charge on the sphere was equal to 0. So finally also, because of this conservation, the charge on the sphere should be equal to 0. So therefore option number D is the correct one. Is correct. Next question. It was also asked in the year 2007, and it states that a circuit is connected as shown in the figure with the switch S is open. When the switch S is closed, the total amount of charge that flows from Y to X is. A basic figure is given to us. So we have S as switch. Initially it is open, and we are having two capacitors, 3 and 6 microfarad, and the resistance is 3 and 6 ohm, and the voltage source of 9 volt is connected. Okay. So initially it is given that switch S is open. So we are given, we have a initially switch S is open, and if switch S is open, therefore we can say that steady state with respect to capacitor have been reached. Therefore we can say steady state is reached, and which basically means the capacitors are fully charged. Steady state means the charge on the capacitor is maximum, and under this condition no current will flow through the capacitor branch or through the capacitors. So you can say capacitor acts as open circuit. So we can just redraw the figure, and the capacitors both will be acting as open circuit, and switch is also open. So the circuit will be something like this. Let us call this as C1, C2, R1, R2, and V is the voltage source. So we have C1, C2 both are open, switch S is still open, resistance is and R1 and R2, and we have a voltage source V which is given as 9 volt connected to the circuit. So therefore the current that will be flowing through the circuit will be entirely through both the resistances. No current will be flowing through this part. Therefore we can say if I is the current that is flowing, therefore we can say our I will be equal to V upon R equivalent. Here R equivalent is the series combination of R1 and R2. So our R equivalent is equal to R1 plus R2. So we can write our current I, voltage is given as 9, and this resistance here 3 and 6. So this comes as 3 plus 6, which gives us the current that is flowing is 1 ampere. Okay. And now we come to the next part, that when the switch S is closed. Switch S is closed. So in this condition also we can draw an approximate figure. So now this switch S is closed. We have resistance here R1, and the end is we having a resistance capacitance C1, C2, R1, R2, and we are having a voltage supply V that is given 9 volt. So therefore if we look to the circuit, when the switch S is closed, we can clearly see that the potential drop across C1 is equal to the potential drop across R1. Similarly, potential drop across C2 is equal to potential drop across R2 because they are parallel with each other. Therefore we can say that potential drop C1 is equal to potential drop R1. Okay. And through our, we already know the current flowing through is our here is our 1 ampere. Therefore we can say that the potential drop across R1, we can just write it directly here. This will be equal to, let us call this as VC1. So VC1 will be equal to our VR1, and that is equal to 1 multiplied by 3. So this comes as 3 volts. And based on this, we can easily find out the charge on C1. So we can say charge on C1 let us suppose that is our Q1, and that is equal to VC1 multiplied by its capacitance C, and this comes as 3 into 3, this comes as 9 microcoulomb. Similarly, we can solve for our C2 also. So we can say potential across C2 will be equal to potential across R2, and this is 1 multiplied by 6, giving us 6 microvolt. Sorry, not micro. This is 6 ohm. I think this will be 6 volt. Similarly, we can find out that the charge, that is Q2, will be equal to VC2 multiplied by C, and VC2 is over 6, and this we are having 6 microfarad, so this comes at 36 micro Coulomb. And we have to find out the charge. So we can say the shift, the charge passing through the switch passing through switch, and that will be equal to our 36 minus 9, giving us 27 micro Coulomb. So the option is C is the correct option. Option C is correct. Next question. We are given a spherical portion has been removed from a solid sphere having a charge distributed uniformly in its volume as shown in the figure. The electric field inside the emptied space is. So basic figure is given to us, and it has a small portion that is being removed. So we have to find out the electric field in this emptied space. So for that, we just can, you can say, consider, let us redraw this figure, and we have a larger sphere, and inside it we are having a small sphere portion that is removed. Okay. And in this, let us suppose O is the midpoint of the sphere, and here O prime is the midpoint of the part removed. And in this, let us consider a point P inside the sphere where we are going to find out the electric field. And we are given that uniformly charge distributed. Okay, for the sake of convenience, let us assume that the charge distribution in this complete sphere is having a charge density of sigma. Okay. And inside this, let us suppose the charge density is our plus and minus sigma. Okay. So for the sake of clarity, we can redraw this entire figure into two parts. One, we are going to assume that it is consisting of a complete sphere with the center O, and this is our, this point is P is somewhere here, and the charge density, for the sake of, let us assume that there is a positive charge throughout the sphere uniformly. So that's why we call that charge density, let us suppose, is our plus sigma. Okay. And we can redraw this small sphere, this small portion that is removed, somewhere like this. So this is small portion that is being removed, and its center is our O prime, and we have this point as P, on which we are going to find out. And here we consider that here the charge density is minus sigma. So we consider that this sphere is having a radius of capital R, and this point P is at a distance of small r from the center of the circle. Okay. And charge density, we already decided that its charge density is equal to rho, then this rho will be equal to, suppose the charge is uniformly distributed, is given as Q, so that will be charge density rho will be equal to Q upon its volume, that is 4 by 3 pi r cube. And we can find out what will be the electric field on this sphere. So first we found out here the charge density, and we can further find out that of electric field that is of inside at a distance r will be equal to K multiplied by charge, and this is our r cube, and multiply by small r. And we can easily substitute value of this capital Q. So electric field inside will be given as a rho small r divided by 3 epsilon naught. And if required vector notation, we can just write it for vector also. And similarly, we can say that, okay, and the direction of electric field we can also point out. So this is our point O, and this is our point P, and distance vector, radius, this distance vector is this direction. Therefore, we can say that our electric field will be something in this direction. Okay. Similarly, we can write for the smaller sphere also. Okay. So this entire was for big sphere. And we can calculate for the small sphere also. And small sphere, we have its center as O prime, and this is our point P. Let us suppose it is at a distance of R2. And we have with this as negative charge density as minus rho. So let us call this as E1. So we can write this as E2 will be equal to minus rho, and we have this as R2 divided by 3 epsilon naught. Okay. And direction, we can just, this will be giving us our E2. Now we need to find out the net electric field. Okay. And the net electric field, let us draw only the points, so that will be much more easier. So we had our point O, that is the center, and there was center of the small circle, a sphere, which is removed, that was O prime. And then we assumed a point P somewhere here, and distance from O prime to P is we consider this R2, and from O to P we considered this as our R1. So we can just use the vector law. Let us call this as our R. So from here we can say that our R1 is equal to R plus R2, which gives us that our R will be equal to our R1 minus of R2. And net electric field, that is our E, will be equal to E1 plus E2, and we substitute the values. R1 divided by 3 epsilon naught minus sigma R2, and this is our 3 epsilon naught. So we can take common, this comes sigma upon, rho upon 3 epsilon naught R1 minus R2, and this is nothing but our R. Therefore, we can say our electric field is equal to 3 epsilon naught times our R. And obviously it is non-zero, we are clearly this, and option number B will be the correct one. Option B is correct. Next question. And it was also asked in the 2007, and it states that a long hollow conducting cylinder is kept coaxially inside another long hollow conducting cylinder of larger radius. Both cylinders are initially electrically neutral, and we have to find out how the potential difference is going to vary with respect to their charge densities. Okay, everywhere it is mentioned. So let us draw the basic figure. So we have two cylinders and both are coaxial. Let us suppose this is our internal cylinder, and coaxially we have another cylinder, something like this. So let us consider these options one by one and try to find out which one of them will be the correct one. So in the option A, it states that potential difference appears between two cylinders when the charge density is given to the inner cylinder. Okay. So the charge density is given to inner cylinder. For the sake of convenience, let us assume that is charge density of plus sigma is given to the you can say internal cylinder, and because of the induction, a negative charge density will be automatically induced on the outer cylinder. Okay. So let us call this as 1 and this is 2. So you can say, or V1 or V2, much more easier. Okay. And because of this, there will be an electric field that will be associated something like this, and because of this we can easily draw a conclusion that the potential difference, that is our delta V, will be existing between our internal and external resistance. So option number A is correct. Option A is correct. In B, it states that potential difference appear between two cylinders when the charge density is given to the outer cylinder. So in the second case, it says that charge density is given only to the outer cylinder. Okay. So we say for the outer cylinder, let us assume that the charge density is given to the outer cylinder, and that is our plus sigma, and here let us suppose the voltage, because the potential because of this is our V1, and we know inside a charge, you can say a conductor, there will be a potential difference, potential, let us assume that is our V2, but because of the conducting nature of the cylinder, V1 is equal to V2. Okay. So if V1 is equal to V2, so we can say our delta V, that is our V1 minus V2, we are only interested in magnitude, will be equal to 0. Okay. So option B is incorrect. Third option states that no potential difference appears between two cylinders when a uniform line charge is kept along the axis of the cylinder. Now in this case, the uniform line charge is kept along the axis. So axis, let us suppose, is given as a positive charge. Okay. And obviously there will be, you can say, because of the, how can you put it, because of the as we move away from the center of the cylinder, the electric field will be different at different point. Okay. Which means let us call this as 1 and this as 2. So electric field at 1 will be greater than electric field at 2. So because of this, we can say that the potential difference delta V will not be equal to 0. And it says that no potential difference. So therefore option C is also incorrect. And finally, it states that no potential difference appears between two cylinders when same charge density is given to the both the cylinders. Okay, so same charge density, and let us suppose here we are given plus sigma, and here is also given as plus sigma. We call this as V2 and this as V1. Okay. So from the, you can say, figure itself, we can see that our the distance, there is some, you can say, distance between the two, or in the simpler words we can say that our V1 is inclusive of V2, inclusive of V2, or with respect to equation we can write that V1 can be written as V plus V2, and therefore delta V will not be equal to 0. Okay. So we can say potential difference is going to exist. Option D is also incorrect. So this is general, you can say, based on the basic how the charge density results in the variation with respect to the electric field. Next question. It was asked in the year 2008, and it states that a parallel plate capacitor C with plates of unit area and separation D is filled with liquid of dielectric constant K is equal to 2. The level of liquid is D by 3 initially. Suppose the liquid level decreases at a rate of constant speed V. The time constant as a function of T is. So basic figure is given to us. Basically this is a RC series circuit. RC series circuit. And for the time constant for RC series circuit, we know tau is equal to R multiplied by C. But for this particular question, this value of C is changing. Okay, because the liquid which is acting like an electrolyte is decreasing with the speed V. So as the C is time dependent, obviously the time constant for this particular circuit will be also our time dependent. And here we are given a unit area, separation is given as D, and initially level of the liquid is given as D by 3. So for any particular time t, we can just draw the capacitor only, because value of R will be same, the value of capacitor is going to change. So we only draw the capacitor part, and at any time t, we know that this total thickness distance between the plates is given as d, and initial separation between this liquid is our d by 3. And suppose at any time t, the liquid is somewhere here. So this is at time t. So obviously, if it is decreasing with respect to velocity v, then this distance will be equal to v multiplied by t. So let's find out the thickness of the liquid at any time t. You can say thickness of liquid at time t, and initially that was d by 3, and it moved a distance of vt in time t. So this is the thickness of liquid in time t. Similarly, we can find out the distance, the thickness of the air. So we can say thickness of air, and that will be equal to total thickness d minus d by 3 minus vt, okay, because now the liquid is at this position, and this can be written as, this comes as 2d by 3 plus vt. Now at this particular, we can divide this capacitor into two parts. We can just redraw the figure, and this is the liquid level at time t, and we just found out, let us rename it, thickness of liquid. So let us call this as thickness of liquid, and this is thickness of air. So this comes as thickness of air, and this is our thickness of the liquid. So now we are having two capacitors. Okay. So one will be consisting of the liquid part. So this is our liquid. Liquid is nothing but a dielectric, and the rest is our air. So for the air, for the liquid, let us call this as capacitor our C1, and this is having a capacitor of our C2. Okay. And it is connected something like this. So we can say that capacitance of liquid part, that is our C1, capacitance of liquid part, that is our C1, and we know that is our K epsilon naught A, and its thickness is given as d by 3 minus Vt, and area is given as unit, value of K is given as 1. So therefore we can write that our C1 will be equal to K is given as 2. So this comes as 2 epsilon naught. A is our unit, so this comes as d by 3 minus Vt. Similarly, we find out our capacitance of air part. Capacitance of air part, which we call as C2, then the C2 will be our epsilon naught A, and the distance is our 2d by 3, and this is our plus Vt, and area is our unit. Therefore we can write our C2 will be equal to epsilon naught 2 by 3 plus Vt. And both these capacitors, we can just draw them for the sake of simplicity. So these are the two capacitors. This is our C1, which is a representation of air. Sorry, C2 is a representation of air. And this is our C1, which is a representation of the liquid. And both are in our series. And this is connected with the resistance R. So we can find out our equivalent capacitance. 1 upon C equivalent will be equal to 1 upon C1 plus 1 upon C2. We can just substitute the values. C1 is our liquid, and we can write this as 2 epsilon naught, and this comes as d by 3 minus Vt plus this is epsilon naught, and it comes as 2 d by 3 minus Vt plus Vt. This comes as 1 upon C equivalent. Now we can just take the LCM. We get this as 2 epsilon naught, and it comes as 2 by 3 minus Vt, and this will be our 2 multiplied by 2 is our 4d3, and this comes as plus twice Vt. Which can be further written as 2 epsilon naught, and twice Vt will be coming as Vt, and this comes as 3 plus 4 plus 1 5. This comes as 5d by 3 plus Vt, and this is our 1 upon C equivalent. So therefore we can say our C equivalent will be equal to 2 epsilon naught, and we can write this as 5d plus 3 Vt divided by 3, which gives us 6 epsilon naught 5d plus 3 Vt. Now time constant. Time constant tau will be equal to R multiplied by C equivalent, and R is a simple R. C equivalent, we just found out our 6 epsilon naught, and we have 5d plus 3 Vt. So the option number 6 epsilon naught R 5d plus 3t, option number A is the correct one. Option A is correct. Next question. It was asked in the year 2009, and it states that 3 concentric metallic spherical shells of radius r, 2r and 3r are given charges q1, q2, q3 respectively. It is found that the surface charge density of the outer surfaces of these shells are equal. Then the ratio of the charges given to the shell q1, q2, q3 is. So we have to find out the ratio. And specifically it is mentioned the surface density of the outer surfaces of these spherical shells is same. So let us draw an approximate figure for that. So we have a inner shell. Suppose this is a center and its radius is given as capital R. Then we have the secondary shell whose radius is given as 2R. And finally we have a third shell whose radius is given as 3R. So this is our 3R. And here we have to remember that the outer densities are equal. So let us assume, or rather we can say be given, that Q1 is the charge on the innermost, that is our R. Okay. And Q2 and Q3 has a surface charge. So this inner surface charge in this first one is given as a charge of plus Q1. So because of this, the inner side of the second is going to have a charge of induced charge of minus Q1, and therefore the total charge on the surface, outer surface, will be of this second one. Let me call this as first, second, and this is our third. So here we are going to get Q1 plus Q2 because Q2 is already present there. Okay, Q2 is already present here. And similarly, because of the charge on this 2, that is Q1 plus Q2, internal side is now going to have a charge of Q1 plus Q2, but because of negative side, and the outer will be equal to Q1 plus Q2, and third is already having a charge of Q3, so this comes as plus Q3. So this is basically your charge distribution, how it is going to behave itself. Okay. So it is a combination of internal, external, internal, external. Okay. And it is given that the surface charge density, outer surface charge density of each is equal. Okay. So we are given that, or let me write that total charge on outer surface for shell 1 will be equal to Q1 for shell 2, that is our Q1 plus Q2, and shell 3, that is our Q1 plus Q2 plus Q3. And for shell 1, let us assume that the surface charge density is our sigma 1, here it is our sigma 2, and here it is our sigma 3. Therefore, we can write that the surface charge densities, surface charge densities for shell 1 which we assumed is our sigma 1 will be equal to total charge, and this is our 4 pi r square. Shell 2, that is our sigma 2, charge is Q1 plus Q2, and the radius is twice, so this comes as 4 pi 2r whole square. And for shell 3 we have sigma 3 is equal to q1 plus q2 plus q3, and this comes as 4 pi and radius is given as 3r whole square. But we are given that sigma 1 is equal to sigma 2 is equal to sigma 3. Therefore we can write that our q1 upon 4 by r square plus this comes as q1 plus q2, and we can just reformulate it into 4 times 4 pi r square is equal to q1 plus q2 plus q3. Similarly, we can write this as 9 times 4 pi r square. And now we can just easily find out their ratio. If we sort it out, we can write this as q1 is equal to q1 plus q2 divided by 4 is equal to q1 plus q2 plus q3 divided by 9. So we are going to use first two, and then we are going to use this first and last and try to solve it out. So we can say our q1 is equal to q1 plus q2 divided by 4, which gives us 4 times q1 is equal to q1 plus q2. This gives us that our q2 is equal to 3 times q1. First part. Second part, q1 is equal to q1 plus q2 plus q3 divided by 9. And we can write this as 9 times q1 is equal to q1 plus q2 is our 3q1 plus q3. So this gives us that our q3 is equal to 3, 4, and this comes as 5 times q1. And the ratio is now q1 is to q2 is to q3 will be equal to 1 is to 3 is to 5. Yes, so we get this as 1 is to 3 is to 5. Option B is the correct one. Option B is correct. Next question. It was asked in the year 2009, and it states that under the influence of Coulomb field of fixed charge plus q, a charge minus q is moving around it in an elliptical orbit. Find the correct statement or statements. So here we are given that we have fixed charge plus q and the minus q is moving in the elliptical orbit. So we can just draw, this is our elliptical orbit and minus q charge is moving. So this is our minus q and it will be moving somewhere here along velocity v, and this is our plus q charge. And this is, if you see this graph, this picture clearly, this is a representation of our Kepler's law. Okay, but for forces here will be electrostatic. Okay. You can say that this is our Kepler law, but forces are electrostatic forces. electrostatic forces. And we know electrostatic force, the standard formula. You can say the electrostatic force, or which we call also as Coulomb force, Coulomb force, which is our F, will be equal to 1 upon 4 pi epsilon naught q multiplied by small q divided by our r square, and this is our r unit vector. Okay. And we know this Coulomb force is nothing but conservative force. This is our conservative force. Okay. And here the orbit is elliptical and the q1 is located one of the force. Okay. Therefore, the charge q, because the distance of this charge q is going to vary. Okay. At any given point, it will be something like this. So we can see the distance of this r, and after some time it will be somewhere here, and later on it will be somewhere here. So this r is going to vary. So therefore we can say the force is also going to change. So in the first part it says that the angular momentum of the charge minus q is constant. And here our, you can say, the force, which is represented as F, always points along the radius vector. Always points along radius vector. Therefore, the torque, whose formula is our tau, is equal to r cross F, will be equal to 0. So radius vector means, in this case both charges are opposite, so this will be attractive, so force will be acting along this radius vector. So therefore we can say that the angular momentum will be conserved. Angular momentum is conserved. So therefore option A is correct. Option A is correct. Next, it says that linear momentum of the charge is constant. Okay. But we can say that because of the force, the particle will be accelerating, and the direction as well as the magnitude of the momentum is going to change continuously during the orbit. Okay. Direction and magnitude because linear momentum is, you can say, dependent upon its velocity v, and from the Kepler law we can clearly see that because of the area swept, when it comes nearer, it has to clear a more area as compared to when it is the farther one. So the velocity is going to vary, and accordingly the momentum is also going to change. So you can say direction and magnitude of momentum changes continuously. Therefore, linear momentum is not conserved. So option number B is incorrect. Next, it states that angular velocity of the charge is constant, and which is also incorrect. Okay, because we know as this charge will be coming, you can say, closer to this plus q, it is going to move with the faster velocity v. This is also called as a pedigree, as well as the sorry, not pedigree, but perigee and OPG. So lower farther point is OPG and closer point is our perigee. So at perigee, the velocity v will be on the higher side, and OPG, the velocity v will be on the lower side. Okay. So you can say that the charge moves faster when closer to plus q, and which we also called as a perigee, and slower when further. Which we also call as a apogee. Therefore, angular velocity is not constant. Not constant. So option C is also incorrect. And finally, we come to the linear speed, and we just from here also we can make a conclusion that the linear speed is also not constant. Linear speed is not constant. So option D is also incorrect. We go to the next question. It was also asked in the year 2009, and it states that a disk of radius a by 4 having a uniformly distributed charge 6c is placed in the xy plane with its center at a by 2, 0 and 0. A rod of length a carrying a uniformly distributed charge 8 coulomb, 8c, is placed on x-axis from x is equal to a by 4 to x is equal to 5a by 4. 2 point charges minus 7c and 8c are placed at a by 4 minus a by 4 0 and 3a by 4 minus 3 by a by 4 and 0 respectively. Consider a cubical surface formed by 6 surfaces where x, y, z both all the 3 coordinates are plus minus a by 2. It means the center will be perfectly at the origin. The electric flux through this cubical surface is. So we have to find out the electrical flux. For that, we are going to use the Gauss theorem. And Gauss theorem, we know, is Q enclosed divided by epsilon naught. So we have to find out the charge enclosed by this cube. Okay. So one by one. So first of all, we can just draw this figure on the larger scale so that we are able to understand it clearly. And we have a cube. There is no need to draw this a two-dimensional because the z coordinate is given as 0. Okay. So we can just deal it with by only two-dimensional. Okay. So this is our x-axis and this is our y-axis. We are given a sphere and this edge is given as, this will be our minus a by 2, this will be plus a by 2, and here also minus a by 2, and here we have our plus a by 2, and we are given a sphere, a circle, a sphere. A disk is given, and disk is given, and its center is at minus a by 2. So center of the disk is somewhere here. So this is the disk, and this is the center of the disk. And then we are given the rod which goes from a by 4 to 5a by 4. So let us draw the rod, and the rod starts from somewhere here. So this is our rod. So this coordinate is our 5a by 4, this coordinate is our a by 4, and this we already know is our a by 2 plus a by 2. Along with this, we are also given two charges. One is our minus 7, another one is our 3. And minus 7 is minus a by 4 and minus a by 4. So x is our a by 4 and y is our minus a by 4. So we can say the charge is somewhere a by 4. So it will be symmetrical somewhere here. So this coordinate will be our a by 4 and minus a by 4. A by 4 and minus a by 4. And this charge is our minus 7, and 3 Coulomb is given as 3a by 4 and minus 3a by 4. So y, one second, I think this might be minus 3a by 4 and 3a by 4. Okay, it means they are on the same side, but in the figure they are given on the opposite side. Hopefully, I'm not sure, might be these coordinate must be same. I think so, because as per the figure this is our minus and this should be our plus. Anyways, it doesn't matter, okay, because if we see closely, whether we take in a downward upper direction, this charge will be always on the outside. Okay. So is our minus 3 by 4 and plus 3 by 4. So it will be somewhere here. This is our 3a by 4 and minus 3a by 4, and this charge is our 3c, and this charge is minus 7c. Even if it is on the upper side here, it will be still on the outside, so it doesn't matter. So let's find out for the disk first of all. So from the disk we can clearly see that only half of the disk is inside the loop, and this is about A, B, C and D. Therefore we can say that disk, and the charge is given uniformly, so we can say disk of charge that is given as 6 Coulomb. Therefore you can say its center is minus a by 2, and from here we can say only half of disk is inside, or we can say part of closed loop. That closed loop is our A, B, C, D. So therefore the charge contributed by the disk, that is QD, will be equal to 6 divided by 2, which will be coming as 3 coulombs. Okay, only half of the charge will be converted by the disk. Now let's consider the rod. So we are given a rod of charge 8 coulomb. A rod of charge 8 coulomb, and it starts from x is equal to a by 2 and ends at 5a by x is equal to a by 4. X is equal to a by 4 and ends at 5a by 4. So it means only this portion of the rod will contribute, or we can say will be the part of the loop. So let us call this a rod as P, this is Q, and this is R. So rod of charge, therefore we can say that only part of rod, that rod is PQ, is part of the loop, that is of A, B, C, D. Therefore we can write the charge contributed because of the rod, let us call that as QR, will be equal to total charge, and total length is our 5, okay, total length is 5 by, sorry, let me write it, length of the rod, that will be equal to 5a by 4 minus a by 4. 5 by 4 minus a by 4, this comes as a. So a is the total length of the rod. And the rod which is inside the loop, we can find out it, length of rod inside the loop. Length of rod inside the loop, and that is our we are only interested in this portion, that is the length of the rod, that is our L1. And total, this is our a by 2, and so obviously this will be our a by 4, so L1 will be equal to our a by 4. L1 is equal to a by 4, and total length is our a. Now we can easily find out the rod contribution, that is charge contributed by the rod will be equal to our total charge, and this is inside, and its total length. So we get this as A goes with A and this goes by 2. So we get this as 2 Coulomb. And now we come to the point charges. So point charges, that is our minus 7 Coulomb, and its coordinate is given as A by 4 and minus A by 4. Yes, and it is inside. And next is our plus 3. Coordinate is given as 3A by 4 and minus 3A by 4. Need not to write the Z coordinate, we will deal with 2D only. And this is our outside. So therefore, the point charges which will be contributing, that is our Q of P, will be equal to minus 7 coulombs. Now we can easily find out the total charge enclosed. Total charge enclosed, let us call that as Q enclosed. That will be equal to our Q of, that was our circle, Q of disk plus Q of rod plus Q of point. This gives us 3 plus 2 minus 7 is equal to minus 2 coulombs. Therefore, flux and by Gauss law. Will be equal to, flux is equal to charge enclosed divided by epsilon naught. This gives us that flux is equal to charge enclosed is minus 2 epsilon naught. So this is our flux. So we get this as option number A is the correct one. Option A is correct. Next question. I think this was the last one. Yeah, so this completes all the 9 questions, and these questions were from the year 2007, 2008 and 2009. So this complete all the 9 questions. Thank you.